Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. We are still in Chapter 7, Bending, and so what we are going to do in this video is to derive the Flexure Formula, which will be useful to calculate the normal stress within the beam that is subjected to bending. So what we saw in the previous video for this chapter is first how to calculate the internal shear and the internal moment in a beam that is subjected to bending as a function of the external shear force and external moment that are applied to this beam. So that's going to be the first ingredient that is going to be useful. And then in the previous video, we saw how to calculate the moment of inertia of the cross-section of the beam, which is going to be the geometrical quantity depending on the shape of the cross-section of the beam that will dictate its resistance to bending. And so based on those two things, and specifically based on the internal moment and based on the polar moment of the moment of inertia, then we will be able to calculate the normal stress sigma in a beam subjected to bending, and this is going to be enabled by the Flexure formula, which we're going to derive in this video. So now what we're going to do is to derive the Flexure formula based on first principles. So we're going to consider a general case. So let's consider the following case where you have a beam like this that is with a given longitudinal axis x, and so y is the vertical direction, and then the z-axis would be coming towards you like this. And so we're going to assume that the beam has a length L along the x-axis like this. And so we're going to see first what is the deformation of this beam due to bending. So before the deformation, if this beam is initially a straight line, after the deformation, after it is subjected to bending, what used to be a straight line is now going to become a curve. So for example, the beam might become like this. So that's going to be the shape of the beam. It's going to turn into a smiley face like this, where the x-axis that used to be a straight line is now becoming a curve like this. So if we want to look at what happens, we need to isolate a small section of this beam. So we're going to take a portion of the beam between x and x plus dx. So initially this section of the beam is going to be a rectangle like this, and after the deformation it is going to turn into something like this. So this is going to be the same portion between x and x plus dx after the deformation. So if I compare this position, this portion of the beam before and after deformation, so if I'm going to look at, I'm going to put the beam after deformation like this on top of the shape before deformation, what you see is that some parts of this beam look like they are under compression. Why? Because if you take this length here, this length is going to become smaller after the deformation as compared to the length it had before the deformation, while on the other hand, some of the part of this beam are going to be under tension because this length now becomes longer than its initial length before the deformation. So in this case, when you have a beam that has a smiley face like this, the top part of the beam is going to be under compression and the bottom part is going to be under tension. So it means that if the top part is under compression and the bottom part is under tension, there has to be somewhere in this beam, somewhere a fraction of this beam that is not under tension, not under compression, that is going to be with no stress. If you have a gradual transition from a compressive stress at the top to a tensile stress at the bottom, then there has to be somewhere in this beam where there is no stress. And so the way you can find this is the position at which the length here would not change before and after deformation. So if you look at this length here in this case, this length in the middle of the beam here, it's the length of this portion of the beam before deformation and after deformation remains the same, which means that this fraction of this beam here will not be under tension, will not be under compression. So that's going to be the portion of the beam that has no normal stress. So if we zoom in a little bit on what's happening here, if we zoom on this isolated section of the beam between x and x plus dx. So let's zoom a little bit more on what happens before and after the deformation again. So let me first look at this portion of the beam between x and x plus dx before any deformation. So it looks like this. So the width here is dx, and so you have the axis x that is going like this. And what we are going to do is to here define a few quantities. We are going to define for any point m belonging to this beam, we are going to say that the point m is going to be at a height y from the axis x. So y is going to be the height of the point m with respect to the x-axis. And we are going to define at the point m what is the length of this portion of the beam at this point m. So what is this length here? And we are going to write this length as ds. So now if I draw the same beam after the deformation. So after the deformation, now it's going to look something like this. This is going to be the same beam that now is being deformed due to bending. So if I look at the same beam, so now you have the axis x that is going like this, and for the same point m within this beam, now it will this length here will now have a different length, which I'm going to write ds prime. This is going to be the value of this blue length, the width of this portion of the beam after the deformation, still at a distance y from the x-axis. So here in this case, necessarily, there again we said that the top part of the beam is going to be under compression because the distance ds prime is decreasing. So the top part will be under compression. And then the bottom part, because now ds prime is going to increase as a function, as with respect to ds at the bottom is going to be under tension. So there has to be somewhere a portion of the beam that is with no stress. And the portion of the beam that is in no stress is where the length, the thickness of this fraction of the beam doesn't change. So for example, let's assume that this is this length here. So this length here, how do I know that this point is within no stress? Is that if I look at the initial length here, which is dx, after the deformation, this length is also going to be dx. So what it means is that there is when you look at the middle of this beam, the length, the thickness of this portion of the beam doesn't change. And why is that the case? Is that when you take the entire beam, so when you take this entire beam here and you subject this beam to bending, what bending will do is to turn the beam that used to be a straight line into a curve. But bending will not change the length of the beam. On average, the length of the beam remains the same. The beam is not going to become longer or shorter because of bending. So if you look at along the longitudinal axis, along x, the length of the beam along the x-axis doesn't change. The only thing that changes is that because of the bending, the top part of the beam here is going to be smaller. It's going to be under compression, and the bottom part of the beam, in this case here, is going to be now under tension. But if you look now along the longitudinal axis, the length of the beam doesn't change, which means that in this case, its new length after the deformation is still going to remain dx. So this portion of the beam where there is no stress, this is what we are going to call the neutral surface. The neutral surface is going to be the surface within this beam that is in between the top and the bottom where there is no stress. This is what we will call the neutral surface by definition. So now, if we want to define the deformation of this beam, we need to find a way to define how curved this beam becomes. So it used to be a straight line, now it becomes a curve. We need to define how curved, what is the curvature of this beam. And one useful quantity that will be useful to define how curved it is to say that I'm going to assume that this is the portion of a circle, that this beam is now, because it's a curve, we can assume that this is part of a circle, and I can define the center of this circle O. And so one thing that you can define is d theta. This is going to be the angle of this portion of the circle. And the last thing that will be a useful quantity to define is what we call the radius of curvature. So the radius of curvature is going to be this distance here, rho. This is the radius of curvature. So this is assuming that now the beam looks like a portion of a circle. I can define what would be the radius of this circle, and that gives me the radius of curvature. If the beam is completely straight with no curvature at all, then it would be equivalent to a circle that has an infinite radius. So if the radius of the circle is infinite, then it means that this radius is actually just a straight line. So in that case, a beam that is perfectly straight would have an infinite radius of curvature. On the other hand, the more curved the beam becomes, the smaller the radius of curvature becomes. So the radius of curvature is a good way to define how curved the beam is. So if you have a beam like this that is only slightly curved, it is going to be associated with a high radius of curvature. But on the other hand, if the beam now becomes more curved like this, then the radius of curvature becomes smaller. The beam is more curved, so that gives you a small radius of curvature. So the radius of curvature, rho, is a useful quantity to define how curved the beam is. So now, based on those quantities, we can look at how the length ds is changing before and after deformation. So if we look first at this section ds before deformation, so initially ds is just equal to dx. That's the portion of the beam before deformation. It's just equal to the thickness of this portion of the beam, so it's just equal to dx. After deformation, so how do I get ds prime? So what I can say is that this beam is now part of a circle. It's the fraction of a circle. So the first thing I can say is that if I look at this distance here, dx, this distance here, dx, is actually a fraction of a circle. So it's a portion of an arc of a circle. So I can calculate this portion, the length of this portion of circle, as the product of the angle, d theta, in radians, times the radius. If I get the product of the radius times the angle, that gives me the length of this portion of circle. And for example, if the angle now becomes 2 theta, then that would give me the entire length of the circle, that is to say 2 pi times the radius. So if I get the product of the angle times the radius, where rho is the radius here, the radius of curvature, then that gives me the length of this portion of circle, dx. I can do the same for ds prime. So the new length ds prime after the deformation. this is also going to be equal to the angle times the radius. The angle doesn't change, it's still d theta, but now the radius is changing. ds prime is located at a distance y from the axis x. So now the new radius is now rho. It's rho minus y. Now rho minus y. If you remove y, then that gives you the new radius here of that is associated to ds prime. So that gives me ds prime. Again, that's the product of the angle times the radius. So now, based on this, I can calculate the local deformation of the beam at this point M. So for this, I can calculate the strain. So I can calculate the normal strain. So I'm going to define here the normal strain at the point M. And so this normal strain, I can just apply the definition of the strain. The strain is the variation of the distance divided by the variation of the length of this member divided by its initial length. It's new length minus old length divided by old length. That's the typical definition of the normal strain. So in this case, if I want the normal strain at the point M, this strain is going to be equal to the new length, ds prime, minus the old length, ds, divided by the old length, ds. So now I can replace all those quantities. ds prime, so I have it here. This is d theta times rho minus y. ds is the same as dx, but on the other hand, we said that dx is also d theta times rho. And we divide this by d theta times rho, which is again ds, which is equal to dx, and dx is d theta times rho. So based on this, we find the expression of the normal strain at the point M. All the d theta disappear, and then the d theta times rho on the top also disappears. So what you get is simply minus y divided by rho, which gives you the normal strain of the beam at the point M. Where, so in this formula, the y is y denotes the vertical position of the point M. How far is it from the longitudinal axis x, and rho is the radius of curvature. So now the question is, where is this strain maximum? Where is the maximum normal strain? That's useful quantities to define. So in this case, if we look carefully at this expression, what it means is that if the beam is like this, so if you have if you apply a positive moment like this to the beam, and so now this beam is has a smiley face like this. What this expression means is that when you look at y equals 0, that is to say, so when you look at y larger than 0, y larger than 0 means that you are looking at positive y. Positive y means that you are looking at a point M that is higher than the axis x. Then, so if you look at this, it means that in this case, if rho is positive, it means that you have a positive curvature like this. Then if you have a positive curvature, then a positive y means that you will get a negative epsilon. If y is positive, since epsilon is minus y divided by rho, then that is going to give you a negative epsilon. Negative epsilons means that you are under compression. If now you look at a negative y, so now you take a negative y. Since rho is positive, a negative y will now give you a positive epsilon. Positive epsilon means that you are under tension. So if you look at this, the tension will increase with y. The more y becomes negative, the more the beams becomes under tension. So if you want to know the point at which the beam is the most likely to break, the point at which the beam has the maximum tension, the maximum stress, that is going to be at the very bottom here. So if you define this point N, this is the point N for which y is going to be the most negative. And since at this very bottom, since y becomes the most negative, then this is where the stress is going to be maximum. So based on this, the maximum stress is going to be at this point N here that is at the very bottom of the beam. And if I want to calculate the maximum value of the strain, it's going to be when y becomes equal to minus the maximum distance from the longitudinal axis x in this case. So if you are at the point M, let's assume that we will define c being the distance between the very bottom of the beam to the x-axis. In this case, if y becomes equal to minus c, so if y is negative and becomes equal to c, where c is the maximum distance of a point of the beam from the x-axis, then if y becomes minus c, then the maximum strains becomes simply c divided by rho, where c is the maximum distance from the x-axis, and that gives you the maximum normal strain. So based on this, if you combine the normal strain at every point M, and if you combine this with the maximum normal strain, what you can do is to re-express the normal strain. You can come up with now a new expression for the normal strain simply by dividing those two relationships with each other. So if you divide this relationship 1, you divide it by the relationship number 2, then you can rewrite this as epsilon divided by the maximum strain is equal to, so you have minus y, this is for the normal strain. You will divide this by c, and then you have the rho that cancel each other. So that's another way to write the normal strain. You can say that the normal strain epsilon is equal to the maximum normal strain times minus y over c. So that's another way to express the normal strain. It's equal to the maximum strain times minus y divided by c, where y is the distance of each point from the longitudinal axis x, and c is the maximum distance of the point that is at the most bottom position of the beam with respect to the longitudinal axis x. So now, based on this, we have everything that we need to calculate the stress. So to calculate the stress, I can use the Hooke's law. So now I can calculate the normal stress. I know that I can calculate the stress at the point M. I can also calculate the stress at the point N, where the strain is maximum. If the strain is maximum, it means that the stress is also going to be maximum. So at the point M, so you have a given normal strain epsilon. If I want to calculate the stress, I need to multiply this by the Young's modulus. I use the Hooke's law. Now, if you are at the point N, this is where you have the maximum strain. If you have the maximum strain, you will also get the maximum stress. And again, you get this stress by multiplying by the Young's modulus. So again, if you divide those two expressions one by the other, then you get this expression that the stress is equal to the maximum stress times so if you divide let me divide those two expressions. So I can take sigma divided by the maximum sigma. The Young's modulus disappear, so I just get the normal strain divided by the maximum normal strain, but we already said that this is equal to minus y over c. So that gives me another way again to define the normal strain. So another expression that I can use for the normal stress is that the normal stress sigma is equal to the maximum normal stress at the very bottom of the beam times minus y over c. So that's another expression that I can use for the normal stress. So it means that the normal stress again is going to be when y is positive, that is to say when you are on top of at the top position of the beam, then y is positive, that is to say that sigma is going to be negative, that is to say you are under compression. On the other hand, when y is negative, if you are at the bottom half of the beam, then sigma is going to be positive, which means that you will be under tension. So far I have an expression for sigma that depends on y, it depends on the position of the point M, depending on the altitude of the point M, depending on its position y with respect to the longitudinal axis x. But so far, this expression is not directly useful because it still depends on sigma max. So I still need to find what is the maximum value of the normal stress in order to calculate the stress at any other points. So now the second thing that I need to do is to relate this normal stress to the internal loads and internal moments that, that this beam is subjected to. So now what we have is, so we have the stress. We have the stress at each point M belonging to the beam as a function of its altitude y. And so the question is, how can I relate this first to the internal load within the beam? And so the first thing that I can do for this is to try to look at what happens if I cut the beam at a given point. What is the stress that is going to be transmitted by the left to the right or the right to the left at this position x, and to see how this is related to the internal load acting within this beam. So for this, so let's assume that we are going to take a beam and cut it at a given position x, and I'm going to isolate only the left part. So you have your beam like this. I cut it at a given position x. So this is the x at which I am cutting the beam. This is the x-axis here. And so now I want to see what is the force that is applied by the right to the left or the left to the right. So in this case, if I'm isolating the left part of the beam, I want to see what is the force that is going to be applied by the right. So we know that at each point M within this beam, if I look at if the distance at the point M with respect to the x-axis is y, then I can calculate the value of the stress, and the stress is a linear function of y. When y equals 0, then the stress is 0. When y is negative, when y is positive, that is to say when M is on top of the x-axis, then the stress is negative. You are under compression. And when y becomes negative, that is to say when M is at a position that is at the bottom half of this beam, then the stress is going to become positive, which means that now the beam is going to be locally under tension. So if there's a stress, then it means that there is a force that is associated to this stress. So what we can say here is that if there is a stress, then I can calculate the force that is associated to this stress. Why? Because the normal stress is going to be the force divided by the area. So if you define a small infinitesimal surface located around the point M, then if I have a given stress sigma, then I can also calculate what is the force that is applied by the right to the left at this point M by taking the product of the stress sigma times the area over which the force is applied, dA. And so in this case, it means that since I know already that the stress is equal to the minus y over c times the maximum stress sigma max, then it means that I can calculate the small force that is applied by the right to the left at the point M. And so this small force is going to be equal to minus y divided by c times the maximum stress sigma times dA, the infinitesimal surface. So if you look at this, it means that when y equals is positive, then you have a force that is going to be negative. So that means that in this case, the top is going to be under compression. But on the other hand, when y is becoming negative, then the force is now going to be pointing towards the right. And so this force is going to be a linear function of y. That is to say that if I draw the force that is applied by the right to the left as a function of the position y, it's going to show a shape like this, where the force becomes more and more compressive when y becomes larger and larger, the more and more positive. On the other hand, the force becomes more and more tensile, more and more pointing towards the right when y becomes negative. So that is the force dF. So this is the small force dF that is applied by the right portion of the beam to the left portion of the beam at each point M as a function of its position, this vertical position y with respect to the x-axis. So now the question is, now that I have those small forces, all those small forces that are applied by the right part of the beam to the left part of the beam, I also know that if I use the method of section, if I cut this beam here, then I know the total force that is applied by the right part of the beam to the left part of the beam. Why? Because if I cut the beam, if I use the method of section, I cut the beam into two parts, then the right parts act as a fixed support for the left part. So I can say that because the right part becomes a fixed support, there will be three potential forces. There will be the normal load like this, which is the internal load. That's you define the internal load as pointing towards the outside like this. I can define also the internal shear like this, and I have the internal moment like this. That's the internal moment that is applied by the right part of the beam to the left part of the beam. So now the question is, how can I relate the stress, the small force dF, and first the internal load P? So in this case, since the internal load is the total resultant normal force that is applied by the right to the left, I can say that necessarily this internal load P has to be the sum of all the small force dF that are applied at each point M from the right to the left. All those small force dF that are applied at each point M of the cross section from the right part of the beam to the left part of the beam, if I sum them all, I will get the total normal internal load P, because P is the resultant force that will be the resultant force of all those small force dF at each of the points of the cross section. So that's the first thing I can do. So I can calculate the internal load. So let's do that. So let's say that the internal load P at the point X at which we are cutting, I can say that P is going to be the sum of all those forces, or all those forces dF. So if I want to get this, I can say that I will define the cross section A. If I want to get the total resultant force, I can do the sum over all the points belonging to the cross section A. Then I'm going to take the sum of all the small forces dF. So I get the integral. That's a continuous summation. So I can calculate the integral of all those forces dF along the cross section A. And that's going to give me the internal load. So let's do that. I can replace dF by its expression. So it means that now you will integrate df. So some aspect of df are constant and I can take them out of the integral, and some aspect of ds are not constant and depend on the position of the point M along the cross section. So if you look at df, so you have minus y. Y depends on where the point M is located on the cross section, so I cannot take it out of the integral. On the other hand, sigma max, that's the maximum stress at the position x. So this does not depend on the location of the point M. This is just the maximum stress, which is located at the very bottom of the beam. So it doesn't depend on the position of the point M. I can take it out of the integral. And then you have C, which is the position, the distance here between the bottom of the beam to the x-axis. It's also something that does not depend on the position of the point M, so I can take it out of the integral. And then what I have to do is just take the integral over the cross section of y times dA, which is the remaining part of df that I cannot take out of the integral. So if I look at this term looks very similar to the position of the centroid of the cross section. Why? Because I have defined that the position of the centroid is given by the integral of y dA over the cross section divided by the area. That is the definition of the centroid. So this term here is very similar to it's the area times the position of the centroid. On the other hand, I know that the beam overall, if it's subjected to a bending, this beam does not get elongated. The length of the beam along the longitudinal axis does not change. So if the length of the beam does not change, it means that there will be no internal load. The internal load within this beam is necessarily going to be zero. Why? Because bending, the only thing that bending does is to transform a beam that used to be straight into a curve, but that doesn't change the length of the beam. So the beam is still going to have the same length along the longitudinal axis, and if the length of the beam doesn't change, then it means that the internal load is zero. So on the other hand, I can know that necessarily this thing is equal to zero. So if P of x is equal to zero, then necessarily it means that the integral of y dA is equal to zero. And if this is the case, then it means that necessarily the centroid of the cross section is going to be located at zero on the y-axis. So the centroid of the cross section is located at y equals 0. So this is important because y equals 0, that corresponds to what we called before the neutral surface. The neutral surface is the point at which there is no strain and hence no stress. It means that in this case, we can say based on this result that the centroid of the beam is the location at which the stress is going to be 0. Why? Because in this case, so we say that y equals 0. This is where the stress is 0. Based on this expression here, sigma is equal to 0 when y equals 0. So this is the neutral surface. And what we just found with this expression is that the point at which y equals 0 corresponds to the centroid. The centroid is also located at y equals 0. So that means that necessarily, based on this result, we find that the neutral surface of the beam, that is to say the point at y equals 0 where there is no stress, so no tensile stress and no compressive stress, then this neutral surface passes through the centroid of the cross section. It is, if you want to know where this neutral surface is, it passes through the centroid of the cross section. So if you want to know the point of the beam where the stress is going to be 0, you need to calculate the centroid of the cross section, and that gives you the point at which there will be no stress. Based on this expression here, we find that the centroid is the point at which you have the neutral surface where there is no stress. So necessarily, it means that for each cross section of the beam, you calculate its centroid, and that gives you the neutral surface where there is no stress. Okay, so that's the first result, and this is a result that we get based on the internal load. So now what I can do is to look at how is this related now to the internal moment. I can look at how is the stress that I can get, how is this related to the internal moment. So let's have a look at this. So now what I'm going to do is to do the same thing. I'm going to look at the stress at each point M for each position Y, and I'm going to see how I can relate all those small forces dF at each point M of the cross section. How does it relate to the internal moment M at the position X? So why is there a moment that is transmitted by the right part of the beam to the left part of the beam? Why is there an internal moment M of X? There is an internal moment M of X because if you look at those small forces dF, each of those small forces dF are going to be creating a small moment about the centroid of this cross section. So if this is C here, the centroid of the cross section, each small force dF is going to create a small moment that is going to be associated to dF. It's going to create a small moment about the point C. And then if I want to find the total moment applied by the right part of the beam to the left part, I will need to calculate the sum of all the small moments dm that are associated to each of those small forces df. I will calculate all those small moments about the point C and then sum them all. That's going to give me the total internal moment. So how do I get that? So you have all those small forces df. So df, they are equal to, I have already this expression, it's minus y over c times sigma max times dA. And if I want to find the associated moment, so the small moment of F about the point C, so this is going to give me a small moment. For each small force dF at a given point M, it's going to create a moment about C. And so the moment is going to be equal to the force times the arm of the force, the magnitude of the force times the arm of the force. So if you have a small force dF, if I want the moment, I need to take the force times the arm of the force, where in this case, the arm of the force is y. Y is the orthogonal distance between the line of action of dF to the point C, so that's the arm of the force. The last thing we need to figure out is what is the sign of this moment. Is it a positive moment or a negative moment? So to find out the sign of the moment, what we can look at is the two cases. When y is positive, is it going to create a negative moment or a positive moment? So if y is positive, then we say that y positive means that you will get a negative forces. Why? Because when y is positive, then the stress is compressive. You get a negative stress and you get a negative force F that points towards the left. So a force that points towards the left has a negative projection. That's a negative force. On the other hand, when we look at the moment, if y is positive, so that's going to create an anti-clockwise moment about C, which would be a positive moment. So if y is positive, then we said that dF in this case would be negative. And then, so when you multiply dF times y, that would give you something negative. But we know that when y is positive, you should have a positive moment. So necessarily we need to add a minus sign here so that the moment becomes positive. Let's check if this expression is still true when y is negative. So when y is negative, then in that case now df becomes positive. Now df points towards the right when y is negative. So now if I look at this expression, I have y that is now negative. Now df becomes positive. So that gives me a negative number, the product of a positive times a negative number. And if I look at the moment that is created by the force df, it's still going to give you a positive moment about c. It's still going to give you a positive moment. So I still need this minus sign here so that I always get a positive moment, whether y is positive or y is negative. So overall, this is now giving me the expression of the small moment dm that is associated to the force df at each point m as a function of its distance y from the neutral surface. So I can calculate the expression of this small moment by replacing in terms of df. So the small moment that is associated to each force df is equal to, I can just replace df by its expression. So minus df is going to give me y divided by c sigma max dA times y, so you get a y square here. So now necessarily I have the small moment m dm that is created by each small force. Now necessarily if I take the sum of all those small moments, that's going to give me the total internal moment. The total internal moment m of x has to be the sum over all the cross section of all the small moment dm. So if I take the sum over the cross section of all those small moment dm associated to each of the small force df, then I should get the total moment. So let's see what that means. So if I replace this integral, so it means that the internal moment m is going to be the integral over the cross section of dm. So I can replace dm by its expression. It's y squared divided by c sigma max dA. So if I look at what can I take out of the integral, so I have m of x, so y squared, so y depends on where the point m is, since y is the vertical position of m, so I cannot take it out of the integral. So what do I have? So I have c is the point, is the distance between the very bottom of the beam to from the neutral surface. So this is something that is constant. I can take it out of the integral, and then I have sigma max, which is the maximum value of the normal stress. That's also a constant. I can take it out of the integral. So what I end up with is this. So I have sigma max divided by c times the integral over a of y squared dA. So here, if we look at this expression, we have now the integral of y squared dA, which is what we defined in the previous video as being the moment of inertia about z. This is the expression of the moment of inertia about z. So now it means that we have this expression, and that gives us a way now to calculate the maximum normal stress. Why? Because now if we use this, I can say that the maximum normal stress, if I replace this by Iz, then I get that the maximum normal stress is going to give me, is going to be the internal moment m times c divided by Iz, divided by the moment of inertia about z. So this is an important expression because it gives me an expression of the normal strain, of the maximum normal stress in terms of the internal moment times c times Iz. So this is going to give me the maximum normal stress. So based on this, I can calculate the stress at each point y. So how do I get the normal stress for each point y? So I have the normal strain, the maximum normal stress sigma max based on this expression. On the other hand, you can keep in mind the previous expression that we had, which is that the normal strain, the normal stress at each point M of the beam is related to the maximum stress times minus y over c. So by combining those two expressions, then I have now an expression that gives me sigma, the normal strain for every position y along the cross section. And in this case, so I can just replace the normal strain by its expression. So I can replace the normal stress by mc divided by iz times minus y divided by c. So the c disappears. So now that gives me an expression for the normal stress for every position y, which is going to be equal to minus times y times the internal moment divided by the moment of inertia iz. And that gives me an expression for the normal stress. So this is the Flexure formula. So this Flexure formula gives you the value of the normal stress. So it's just to summarize. So what we said is that we have a beam like this, where you have a beam like this, where x is the longitudinal axis. So when you want to calculate the normal stress, you can do it first for each position x. So if you have the beam going between 0 to L, so you can calculate the stress for as a function of x. When you fix the point x at which you want to calculate the stress, then you will need to look at what is the cross section at this position x. So then if you look at the cross section at the position x, then you have two things. First, you will calculate what is the internal moment at this position x. So this is what is going to be this term here. So m of x is the internal moment at the position x. So necessarily it means that the stress will depend on x. So once you have the internal moment at the position x, then you will need to look at the cross section at the position x. So you will need to look at what is the shape of this cross section. So we have the neutral surface here that is for y equals 0. And then, so for each point M within this cross section, if you want to know the stress at a given point M, then you need to look at what is its position y with respect to the neutral surface. And then you can calculate the stress. So the stress at the same time depend on the position x along the longitudinal axis, but then for each of the cross section here, for each of the cross section, you can also move up and down within the cross section. So the stress is also going to depend on y. So it depends at the same time on x, the position along the longitudinal axis, but also on y, which is the vertical position. So the stress depends on both on x and on y. So in this case, so this expression is useful because it's giving you the normal stress within a beam. We can first take a look at the units. So the stress, we expect to get something in Newton per square meter. So if we look at this, we have the moment of inertia, which is in meter 4. We have y, which is the position with respect to the neutral surface, which is just in meter. And then you have the internal moment, which is in Newton per meter. So indeed, you get something where the unit match. Let's look at the sign now. So let's assume that you have a positive internal moment. So remember that the sign convention for the positive internal moment is that it's giving you a smiley face. So if you have a beam that locally is smiling like this, then it means that it's a positive moment. So that's the positive sign convention for the moment, the internal moment. So based on this, what this formula tells you is that when y is positive, then since the internal moment is positive and since the moment of inertia Iz is always a positive quantity, then necessarily sigma is going to be negative, which means that the top is under compression in this case. On the other hand, if y is negative, if you are at the bottom part, and if the moment is still positive, then now the stress becomes negative, which means that now the bottom part is, the stress becomes positive, so the bottom part is now under tension. Now let's look at the other case where now you have a case of a negative internal moment, which is the case where the beam is now having a sad face like this. So again, let's do the two cases, y positive and then y negative. So now if we look at this expression, if y is positive, now the internal moment is negative. So I have a positive number times a negative number plus a minus sign. That is now giving me a positive stress. So now sigma becomes positive. So now it means that the top is under tension if the moment is negative. On the other hand, when y is negative, and the moment, the internal moment is also negative in this case. So you have the product of two negative numbers that gives you a positive number. You add the minus sign that is now giving you a negative sigma, which means that in this case, the bottom of the beam becomes under compression. So based on this, so we have now the Flexure formula. So this is the formula that's going to allow you to calculate the stress. If you think about the different steps that will be needed to calculate the stress for a bending problem, the first thing is that necessarily you will need to calculate the internal moment. So you will need to calculate the internal moment as a function of x. That is going to be something that you can do with the method of section or the integration method, for example, that gives you the internal shear and then the internal moment. So you need to look at what is, as a function of x, the internal moment, to calculate the moment at the point x at which you want to calculate the stress. Then the second thing is that once you have the internal moment, then you need to calculate what will be the geometry of the cross section at this point x. So for this, the first thing that you will do is to calculate the position of the centroid of the cross section. Why? Because the centroid gives you, it defines the neutral surface, y equals 0. So you know that the neutral surface goes through the centroid, so you need to look at where is the centroid. So where the centroid gives you the point at which the stress is going to be 0. It's giving you the neutral surface. So you need to look at what is the centroid of this surface of the cross section at the point x of this cross section here. Once you have the centroid, then you will need to calculate the moment of inertia of the cross section Iz. Keep in mind that this can potentially depend on x. The cross section doesn't have to remain the same for every position x, so this can potentially depend on x. And so once you have this, then you have everything you need. You have the internal moment m. You have the cross section moment of inertia Iz, and then you just need to apply the Flexure formula in order to get the stress for each point x and for each point y. So for each point m, both as a function of its position along the longitudinal axis x and also its vertical position wise. So now you just have to apply the flexure formula as the last step.